Hi, everyone. We're looking at, I'm sorry, this is section 4, so there's a title slide malfunction and made a copy paste error. We're talking about hypothesis testing now. S3 was the last section, so this is actually S4. Hypothesis testing. Sorry about the title slide glitch there. But this is exciting for me because this is where I feel like we're getting into real science, real research. And we're using applied statistics and data science in a way that actual researchers use it, or that's what we're trying to do. So the introduction today goes back to a famous story about called the lady tasting tea. So it turns out that Dr. Ron Fisher, the godfather of modern statistics, and Dr. Muriel Bristol were colleagues at a British research station. This is right after World War One. And they have a meeting because they're on the same research team. They have a meeting, and Ron Fisher is pouring a cup of tea and offers a cup of tea to his colleague Muriel. And Muriel says, "No, thank you." And Ron looks puzzled, when she says, "The tea tastes better when the milk is added first rather than the tea being added first." Okay, so you can read more about the details here. Look up the lady tasting tea on Wikipedia, sure. And you get more details there, but let's explain the chemistry that's going on, right? So if Muriel Bristol can, well, first of all, I didn't know until I heard this story that the Brits add tea to their milk. I mean, add milk to their tea, sorry. I drink coffee, but apparently, like with coffee, tea is a little bit bitter. So sometimes you add a little bit of milk or cream, right? A little bit of sugar. That apparently is part of the traditional British tea. Okay. But now let's think about adding that milk, right? The chemistry and physics involved, right? So if you think of a cup, you pour out a cup of boiling water, essentially, right? So let's say it's 200 degrees. It's just boiled. It's been sitting for a few seconds, and you pour from a 200-degree tea kettle into a cup. Okay, so now you have 8 or 9 ounces of boiling water in a cup, with the tea bag, and you're going to add milk. Okay, well, the milk is in the fridge, let's say 50 degrees. Again, I'm using 200 degrees for the boiling water tea, or just boiled water tea, right? 200 degrees for the tea, 50 degrees for the milk. And what happens? You pour a few drops of milk into that tea, and the temperature of the milk suddenly increases from 50 to 200, right? 150-degree approximately temperature increase in what? In a split second. Okay. And I believe what Muriel Bristol would contend or would have contended is that that there's a slight bit of scalding that happens to that milk when the temperature increases so quickly. But flip it and think of it the other way. What if you pour, let's say, a half an ounce of milk into the bottom of a cup, and then you start pouring tea in on top of it? Now, instead of having 8 or 9 ounces of 200-degree liquid hitting the 50-degree liquid, now we have just a few drops, a few ounces pouring in over time, right? So what happens is the milk still goes from 50 degrees to 150, up 150 degrees to 200 degrees, but the temperature rise happens more slowly. And I think that people agree, people who've thought about it over the years, agree that that's about what happened. And a lot of people didn't know you could taste the difference. Again, it probably takes a very good palate to be able to taste that kind of slight difference if there's just a tiny bit of scalding on the milk. Okay, so that's what's going on, and it puzzled Ron Fisher. So what did he do? He says, "Well, we can test it. We'll give her a blind taste test. We'll give her 8 cups of tea. 4 will be milk first, 4 will be tea first, but they'll be presented in a random order, so she won't know which is which. And if she can taste the difference, she'll be able to separate those 8 cups into 4 and 4, 2 groups of 4, accurately." Okay. And so the idea was, well, if she, well, let me say that they were skeptical that she could taste the difference. I don't think they said I don't think they thought she was lying. I think that maybe they thought she was mistaken or overly confident that she could really taste a difference. Um, but they were skeptical. So they said, okay, let's suppose that she is guessing, right? She's just guessing it, and she has a 50-50 chance of success here. If that's the case, then what's the probability that she would get 6 right, or identify 7 right, or identify 8 right? Okay, and it turned out that Ron Fisher, for reasons we don't know, settled on 7 or more. Okay, and so if she identified 7 correctly or 8 correctly, then her claim would be established beyond question. I'll just throw this out. In hypothesis testing, we have an alpha, which is the level of significance. And basically, Ron Fisher said, let's make it 5%, 0.05. That is the criteria. And if the probability of the actual sample data that we collect has a probability of occurring of less than 5%, then we're going to say, oh, no, 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 no. Muriel can taste the difference, right? So that was the basic idea. And we can do some work on that, and we will. First of all, let's talk about this null hypothesis. So basically, Ron Fisher writes about the story, and he writes about how it inspired this idea. Later, he's on a walk and he's thinking about this, and it inspires the idea of a null hypothesis. And a null hypothesis is a claim that cannot be established but only disproved. Okay. And so in this experiment, like I just explained, assuming the null hypothesis is that Muriel is guessing at random. Okay. Well, what if that doesn't match up to the actual probability of the sample data? They're going to do this taste test. What if the probability of the sample data is very, very small compared to what would be true if the null hypothesis is in fact true? Okay, so just some modern statistics. We have the null hypothesis, which is an H with a subscript 0, and we have an alternative hypothesis, which is an H with a subscript A. Okay, and the null hypothesis is that Muriel's chance of success is probability 1/2. However, the alternative hypothesis is no, she's better than 1/2, 50-50 guessing because she can taste the difference. Okay, so this is in mathematical symbols, but basically she's guessing is the null. She can taste the difference is the alternative. That's the implications. Okay, but if we're going to reject this null hypothesis, right, we're gonna have some evidence pointing to the fact that it's not true, or not, the data aren't consistent with the null hypothesis. So there's this matching or mismatching between the null hypothesis and the actual results, right? And if there's a mismatch, we're saying, well, this mismatch in the data and the null hypothesis indicate that the null hypothesis is likely to be untrue. Okay, so it's a probability-based decision. Okay. And if Dr. Bristol correctly identified 7 or more cups of tea correctly, would you believe her claim? Why or why not? Well, let's talk about that for just a second. I'm going to jump into the notebook for this section, and let me just make sure that we initialize. I have the combinatorics function that we've created. Why? Well, because we're using the binomial distribution, and if you recall, right, if we're doing the number of successes is 6, so we have x equals 6, right? What's the probability of getting exactly 6 successes out of 8 trials? Well, it's 8 choose the number of successes times the number of successes raised to the power, which is the number of successes, right? So the probability of success raised to the number of successes power, and the probability of failure raised to the number of failures power. Okay, so we did that in the binomial distribution section, okay? So let's just throw this in here and see what comes out. And it turns out that there's about an 11% chance of getting 6 right if you're guessing at random, right? So that's the key here. We're assuming the null is true and just running the probabilities here. Okay, well, we have it set up now. We can just change the 6 and go to 7. Oh, and it turns out there's only a 3% chance, or 3 1/8% chance of getting 7 right. Well, what about getting 8 right? Oh, now there's less than 1%. We're looking at approximately a 0.004 or a 0.4%, right? So we're not in a situation that's very likely. Getting all 8 correct if you're guessing at random is less than 0.5% chance of happening. The funny thing is, Ron Fisher tells the story that they have a taste test, and this is what inspires the idea. He writes this in his book, and the book gets published, and then people like me and you start asking the question, well, what actually happened? Because he didn't have the end of the story, the anecdote that led to his idea. He went on a total math geek, right? Went on and talked about all the cool science, all the cool math, all the cool theory he's developing based on this anecdote, but he doesn't ever tell the rest of the anecdote, like how many did she get right? And it turns out she got 8 out of 8. So history tells us, and again, we have some sources outside just this book that Ron wrote that record the story. And by the way, Muriel Bristol's future husband was also one of the two, along with Ron Fisher, who administered the taste test, right? So there are people who knew about this taste test, and we find out about it from other writings. And she got 8 out of 8 correct, which is a tiny chance. Which means what? Which means that this null hypothesis is inconsistent with the actual data from the experiment. And I think that's important. Let me say that again, right? The null hypothesis of the experiment, right, is, and we're using pi to mean probability. That happens a lot in statistics. I know that you think that pi is a number near 3.14, and I think of it that way too. But in statistics, we use pi to indicate a probability. So the null hypothesis here is that the chance of success for Muriel is 1/2. But what happens is, right, we find that the actual results of the scientific experiment have it's a mismatch, right? It's like it's a very small chance of being true if the null hypothesis is true. What's much more likely to be true is the alternative hypothesis that Muriel can taste the difference. Okay, so this is the brilliance of the idea. This is what Ron Fisher decided, that we'd have this null hypothesis that wouldn't be established, but it would be falsified. In general, we're trying to falsify the null hypothesis. Okay, so we can do this empirically as well. If we have this R-flip formula, as you recall, what do we have? I have some code in here for you so you can see, right, that we do R-flip. Okay, probability of half. This summarize equals true gives me this nice table with the number of heads, the number of tails, right? And what does successes 1, 2? Again, remember, this is data frame for row, comma, column. It turns out that this that the output from the rflip function with the summarize equals true is a data frame. All right, so then the data frame notation actually works on these results. What am I doing here? I'm showing you that, yes, the first row, second column, right? This is row 1. This is column 2. So the 3 is coming in the right place. I'm just showing you that the machinery is working here. Okay. And you can see as I hit Control Enter, 4 and 4, 5 and 5, 4 and 4, 1 and 1, right? So this is in fact recording the correct number of successes. And I want to go back up here. Why? Because what we're going to do is we're going to confirm all these probabilities. But you know what? try this. Put 1:8. I'm sorry, I want to do 0:8. Why? Because watch what it'll do. Since x now has 9 different values, starting at 0 and going up to 8, right? What does that do to the formula? Oh, it prints out all of the values. Now, you'll notice that the probability of getting 0 correct is the same as the probability of getting 8 correct. Okay, which makes sense. This is a symmetric distribution. Why? Because the probability of success is 50-50, right? So the probability of getting 1 success out of 8 is the same as getting 7 successes out of 8. Okay, but what do I want to do here? I want to just point out that we've got all these values. Okay, and we'll estimate those in a minute. That's going to be what we do with with our testing. Now we're going to use the for loop from section 2. And let's just take a look at what's going on here. The number of successes starts out as an empty vector. We're doing 1,000 simulations of what? Coin flip, 8 coins. The coins have a 50-50 chance of success. Summarize equals true to get that data frame format printing out of this function. Then what are we doing? Successes is that data frame object, so the row column notation is working to say what? Well, for that particular time through the loop, how many successes there were. How many, well, what we're simulating is the number of cups of tea that were successfully identified out of 8. Okay, so now total successes is our data vector, right? So we get the 95th percentile and the 5th percentile. And notice that I've created this cat function here where we can assess how many successes there are. So let's start with 6. Okay. And what are we doing? We're just counting the number of times there was a 6. And then what are we doing? We're dividing it by the number of trials. Wait, so 6 there and there. So we have the total number of successes. Then we're doing the total number of successes divided by 1,000 to get a p-value. Okay. Then we're creating this histogram based on the total successes. We're drawing blue lines again at the 5th and 95th percentile and run it. Okay. And you see a nice bell-shaped distribution. And you see what we saw from the numbers up above, right? That getting 7 or 8 correct out of 8 attempts is pretty unlikely if you're guessing at random, right? And you can see that with 1,000 trials, our estimate was 0.12. If you recall, right, from above, the actual probability for 6 is about 11%. Let's jump back up here and find it, right? So we're close, right? The empirical value is close. Okay, and let's simulate the situation several times and verify the probabilities above. Okay, so what I want to do, and I don't have a table this time, I just am going to run the simulations. And what am I going to do? I'm going to do 1,000 trials again, but now I'm going to estimate the probability of getting 7 correct. So I have to change the 7s in these formulas. I'll change 7 here in the histogram. Oh, did I get that changed in the histogram up here? So that the title in the histogram matches the actual number of trials that we're looking at. Sorry about that. And again, we can run this again and notice that before we got 12 and now we're getting 10.2% as our estimated p-value, and the actual value is 11%. So we're getting close, not terribly close, but reasonably close. Okay. And now we're doing the same thing, but for 7 successes. Okay, and we're getting 0.04, which is approximately the value we're searching for. Again, jumping up to where we did all of these. The actual p-value, the actual probability is 3.125%, so 3.1%, right? And we get 4% as our estimate, okay? We had 40 successes out of 1,000, so the calculated p-value is 0.04. So this is all going well for us at the moment. We're getting reasonable answers, reasonably accurate answers. So what am I going to do? I'm going to do the same thing, keeping it at 1,000 simulations or repetitions of the simulation. Only now I'm going to change this to 8. And I'm going to change this to 8 and this to 8. And I'm going to run it in 1,000 trials, and our estimate of the p-value is 0.005. Now, the actual p-value is around 0.004. Let's just run right back up and see that up here, right? So 0.0039. Okay, 0.0039 is the actual p-value. And when we scroll back down into our... Okay, so we're not too bad. The actual value is 0.0039, right? So we're what, 6 thousandths away? Our estimate is pretty accurate. Okay. Oh, and it says 7 trials. Let's run this again. um, because I do like my titles to actually match. It's one reason I put them in there so that visually, oh, and look, the p-value now is 0.004. So now we're 1/1000th um, away from our estimate. Okay, and you can see that the 5th percentile, right? So about 5% of the time we're seeing results over like this, and 5% of the time we're seeing results like this, right? So the blue lines are at the 5th and 95th percentile. So each of these areas represents about 5% of the total area under the curve. So you can see that this cutoff matches up to an alpha of 0.05, right? Our level of significance is 0.05. Now, why did Ron Fisher say, okay, if the probability is less than 0.05, we're going to reject the null. We're going to say that we have evidence that Muriel is not just guessing at random. Okay, why did he pick 5%? Well, we don't really know, but let's say this. He picked 5%, it kind of caught on and people started using it, and now that we've been able to test it with over 100 years of use, or about 100 years of use, and in the computer era where we can run these huge simulations billions of times in just a few seconds, it just turns out that empirically the 5% value tends to work really well. In most scientific endeavors, in most of the ways we use statistics, 0.05 is a good alpha. Do we sometimes set alpha differently? Yes, sometimes we set alpha at 0.01 or 0.025 or 0.05, 0.1. It's always low, it's always near 0.05, but a really good standard alpha for an introductory statistics course is 0.05. And experience has borne that out. So that was a good guess on Ron Fisher's part. I don't know exactly why he guessed that. But let's do this. Before we finish up, let's just go increase the number of trials. Okay? So if we're going to go back up to the first one, instead of 1,000, let's do 10,000. And that's also going to require us to update the probabilities calculation. With 10,000 trials, again, remember we're targeting about 11%, 10.9% would be more accurate. It does take it a few seconds. And notice we do get slightly more accuracy. And sorry, this is 6, right? So let me run it one more time. It takes a few seconds. And again, 10.9, I believe, was what we're aiming at. We get 11.09, which is very close. Notice that the breaks in the histogram are not really working out that great with this larger number, but you can still see essentially what's happening. And again, going to 1,000 here. Excuse me, 10,000 and 10,000. 7 is correct. And we can run that. And again, we're not all that accurate, but we're not all that far away either, right? Aren't we looking for 3.9%? And we can do this for 8. So I'm going to go to 10,000 simulations. Okay, and again, we're looking for 0.0039, right? And we're already really close to it, but let's just see what happens. It takes a few seconds. And again, a really nice estimate, and we're getting good accuracy. And what are we using? Well, we can't really change the sample size, right? She tasted 8 cups of tea, so we can't increase the sample size from 8 to 20 or from 20 to 50. Would that improve our estimates of these p-values? Absolutely. But we just can't do it, right? So when the central limit theorem isn't available to us, when the sample size isn't available to us to increase the value, we can use the law of large numbers, which we did just now. You do more simulations, more samples. You don't increase the sample size, you increase the number of samples. All right. And so the second task is about a cross-country team. Okay, so for the UNG cross-country team, and let me jump back into the PowerPoint. Some things that we need to remember as we go forward. We have this null hypothesis. And by the way, it specifies a probability model. That feels a little different later on, but that is in fact what it's doing. You set up a probability model, and then the alternative hypothesis is what is true if the null is false. Again, this has a slight nuance to it, but essentially what's happening if the null is false. Okay? And then the p-value, right? What does the p-value mean? It means that if we assume that the null hypothesis is true, then the p-value is the probability that we would see results as extreme as the ones we have observed just by random chance. Okay, so again, you see Muriel score 8 out of 8, right? And the p-value of 0.004 is what? It's the probability that, supposing the null were true, that results like that would happen. Well, they happen about 0.4% of the time. So when that p-value is small, there's a mismatch between the null and the results, right? The results don't look like they were generated from this supposed probability experiment set up in the null hypothesis. Okay, so those are some key ideas we need to keep with us as we go forward. And remember, when p is small, we're going to reject the null because it appears that the null hypothesis fails to account adequately for what we actually observed in the sample data. Okay, it is based on probabilities, so there are some errors. We'll talk about type 1 and type 2 error. Again, reasoning based on probability is fine, except there's a chance of error, right? And unlikely things do actually occur sometimes, okay? So we already did this in the notebook, so what's the second task about? Well, assume that for the UNG cross-country team, and we have data that's in the notebook. But the key thing here is that for healthy adult women, typically heart rates have a bell-shaped distribution. They're approximately average of 75, standard deviation of 8. Now, that's imperfect. It's an older value, and you know, science keeps updating. And some people may argue these specific values, but it doesn't matter if we're off by a tenth or a quarter of a point, or if the standard deviation is slightly different. What matters is the idea that healthy adult women have a certain range, right? A certain bell-shaped distribution for their heart rates. And why would the cross-country team be different? Well, it turns out that resting heart rate is roughly a proxy for fitness. In other words, the more aerobic fitness, the more the more cardio you do, the more aerobic fitness that you have, um, the lower your resting heart rate tends to be. Like I said, it's a rough proxy. It's not a perfect one. But say marathoners, these are endurance athletes, right? And they tend to have lower resting heart rates. Okay? Strength training doesn't have quite the same effect. Again, it tends to be the endurance athletes that have the lower resting heart rates. Um, well, these cross country team, these females on the UNG women's cross country team, they are endurance athletes. They do a lot of um, aerobic training, right? And I'm not saying they do no strength training. I'm just saying they do a lot of aerobic training, right? So what's our null hypothesis? Our null hypothesis is that, hey, the average mu for the cross country team's resting heart rates is 75. Why? Well, by the way, that 75 value is called mu sub zero, right? It's the value from the population. It's the average value from the population. So until we know there's something different about these cross country teammates, we're going to, the null hypothesis, hey, they're the same as everybody else. They have an average resting heart rate of 75 beats per minute. Okay, what's our alternative? Our alternative is that they have a lower resting heart rate than average. Okay, so this is an actual modern day hypothesis test. So let's jump back in and run it. Okay, and you see here the data. These are the resting heart rates. And I'm going to show you a couple of things. First of all, we're going to verify the assumptions of the t-test. Why? Well, the t-test is the thing in modern statistics that we use to do all of these simulations that you saw in the previous sections to test this, right? We used to use the z-test, which actually used the bell curve. The t-test is an updated modern version of that z-test, which does essentially the same thing, but is more accurate for reasons we will discuss. Okay, so if we're going to verify the assumptions of the test, it turns out there are three of them. Normality, homogeneity, and independence, normality, and homogeneity of the variances. Okay. So let me actually just put those down. So we have normality. Normality is easy. Normality says that the data were drawn from a bell-shaped distribution. Okay, we need to have evidence of that. Well, we can try a histogram or a density plot and verify that. Normality, independence. What's independence? We can't test that statistically. Independence means that no one's score depends on anybody else's score. In other words, if they took a math test, nobody was cheating off of somebody else, right? So the scores have to be independent. Again, this is a research idea, and the research protocols have to be correct so that the independence is upheld. It's an assumption of the statistics being correct, right? If you don't have independently drawn samples, then no, you won't have accurate statistics. But it's not something the statistician can detect or fix. So normality, independence, and homogeneity of the variances, which is basically saying the same standard deviations. Right, that in this case, right, that the standard deviation for the sample of the cross-country runners is the same as the standard deviation of the population. Okay, well, it turns out that in modern statistics, this one tends to be limiting. So we have a way to just we have a way to do the test without that assumption needing to be true. We can't check independence, so what are we going to do? We have the normality assumption to check. Okay, and I don't want to go too deeply into that, but what am I going to do? I'm going to do a density plot for the data. So I'm going to run the data cell to make sure that it's in there. And then what I'm going to do, I'm going to do plot.density.data. Okay. And again, if you want, you can put a title in. Main equals okay. But what do we find? We find, again, we're not saying that it's perfectly bell-shaped. We're saying that there's evidence the data were drawn from a bell-shaped distribution. And we have a little bit of a two-mode thing happening, but the two modes are reasonably close to each other. And so is this generally bell-shaped data? Yes, it is. Okay. Again, I don't want to argue too much. Why? Because I want to show you that we can run this, right? We can run this how? I do t.test is the R function that runs it. I'm running it on the data, and I'm going to tell it that mu equals 75. I have to tell it this. Why? Because it doesn't know my null hypothesis, right? It knows what the data is here, but doesn't know the null hypothesis unless I say, okay? And there we go. It does all of those simulations that we did up above and generates a p-value for this specific data. Okay? But notice that our p-value is 0.09, right? If I round that 0.08817, which is greater than 0.05. Okay, so what is my result? Right? Because p equals 0.09, which is greater than 0.05, which equals our alpha for the moment. We fail to reject the null. We fail to reject the null hypothesis. We have no evidence that these runners have lower resting heart rates than typical adult females. Let me put that in Markdown, and I can put this inside $sign. So the $sign math is available to us. And if I want alpha to actually be the symbol alpha, I do a \alpha. And now I get a nice equation in here. And so you'll notice that there are two different statistical conclusions. I'm either rejecting the null, like Ron Fisher did in the lady tasting tea experiment. Here, I'm failing to reject the null. Why? Because our calculated p-value was greater than 0.05. Okay, when our calculated p-value is greater than 0.05, we fail to reject the null. Why? Well, we don't have great evidence that the null is false. Okay. So those are the two statistical conclusions: reject the null and fail to reject the null. All right, and we'll learn how to interpret those findings as we go forward. So this concludes the introduction to hypothesis testing.